Hello everyone, myself Dr. Krishna Chaitanya, working as a professor in EC department, RSR Engineering College. Now, here I am going to be covering the concepts in electronic devices and circuits that belongs to ECE as well as EEE for first year second semester. Now let us start with the basic concepts in electronic devices and circuits. Then we will go ahead with some of the concepts in the first unit. This is what is the syllabus given in unit number 1. The review of semiconductors, then introduction to the diode, the basic working principles in the diode. Right. Before getting into these concepts, first of all we need to understand what are the different types of materials that are available. The reason is that if you want to go through in depth of the semiconductor devices, first we need to understand how the classification of the materials are done. Then only we can be able to understand the concepts of semiconductors. Yes, most of the people, first they need to understand these electronics plays a vital role in day-to-day life. What is this electronics? Different people give different definitions, but the standard definitions says electronics deals with electrons, the flow of electrons. Otherwise, electronics deals with electronic devices. And few more people says that electronics is a branch of engineering that is going to be dealing about the current conduction in semiconductor material. Now, what are the basic properties of an electron? The first one is charge of an electron, which is 1.602 into 10 power minus 19 coulombs. And mass of an electron is 9.1 into 10 power minus 31 kgs. The radius of an electron is 1.9 into 10 power minus 15 meters. These are the very important properties one has to remember for an electron. The charge, mass, as well as the radius of an electron. Now, in order to understand what are the different types of materials we have, first we need to go through what is meant by energy band diagram. The energy band diagram is consisting of 3 bands. One is a valence band, second one conduction band, and third one is the forbidden energy gap. This is the basic structure for an energy band diagram. We can see here we have a valence band. This is the valency band and this is the conduction band. The gap between the valency band and the conduction band is called as forbidden energy gap. And in the middle we have one more energy level called as Fermi energy level. In the next coming classes we will discuss about what is the purpose of Fermi energy level. Now see, this is whichever is shaded in the blue color. This is a valence valency band, which is having the range of valence electrons. For time being, just remember the naming called valence electrons and free electrons. We will discuss what is meant by valence electrons and what is meant by a free electron. Here, this is what is the energy level called EV, which is represented at the maximum level of valency band. The maximum energy level in the valency band is called valency band energy, here represented with EV, and the minimum energy level in the conduction band is represented with conduction band energy EC. In valency band, EV is represented at the highest energy level. In conduction band, EC is represented at the lowest level. And the gap between the valency band and the conduction band is called as forbidden energy gap. Usually this forbidden energy gap is nothing but the amount of energy required for the charge carriers called valence electrons to move from valence band to conduction band. That is what we represent with forbidden energy gap. Now we will move on to the basic concept called classification of materials. Based on the electrical conductivity of free electrons, we have 3 different types of materials. One is called conductors, second one insulators, third one semiconductors. Let us talk about the first one called as an energy band conductors, that is with respect to the energy band diagrams. Now this is the energy band diagram for the conductor. It is very clear that both valence band energy and the conduction band energy are overlapped. If they are overlapped, the forbidden energy gap which is equal to 0. That's what here the energy level is represented with Eg is equal to 0 electron volt. Here electron volt is nothing but 1 EV which is representing as the energy. The units for the energy is represented in so many number of electron volts. 1 EV which is equal to, we know E is nothing but charge of a electron. That small e you represent or a small q, both small e and small q are representing charge of an electron, and we know that charge of an electron is 1.602 into 10 power minus 19 coulombs into 1 volt. That gives you 1.602 into 10 power minus 19 joules. Means that 1 electron volt is equal to 1.602 into 10 power minus 19 joules. And most popular examples for the conductors are copper, aluminium, and one more best example is the gold, which has a very good conductivity property. But for real-time applications, we are not going to be using the gold because of heavy cost. And these are the two most popular materials that are used, called copper as well as the aluminium. Now, let us come to the second one called insulator. This is the diagram for the insulator. Now, there is exact contrast between the energy diagram for conductors and the energy diagram for insulator. Here you have a maximum gap that is going to be existing between the valency band and the conduction band. Here that is represented with 6 electron volts, and this is a very large energy gap, or you call it as forbidden energy gap between the valency band and conduction band. There is no possibility, and it is very difficult to move the charge carriers from the valency band to the conduction band. That's why you try to apply even the external energy, the charge carriers cannot be able to move from the valency band to the conduction band. Which means that in case of an insulator, the current conduction is approximately equal to 0, though you apply any amount of an energy. And the best examples for insulators are wood, paper, glass, and plastic. And third type of a material which is having the properties of both conductor as well as the insulator is called semiconductor. That's why it is named as semiconductor, which possessing the properties of both conductor as well as insulator. At 0 degree Kelvin, the material behaves like perfect insulator. At normal room temperature, it has some amount of an energy. Thereby, the charge carriers have the sufficient amount of energy to cross from the valence band to the conduction band. At that point of time, the material behaves like conductor. The energy gap, or you call the forbidden energy gap in case of semiconductor, is 1.1 electron volt. And the best examples for semiconductors are silicon and germanium. These are the two popular materials which are used to manufacture the semiconductor devices. Each one has its own advantages and disadvantages, but the most popularly and widely used material is silicon. Now, we move on to our next concept. Now we are confining out of all the three types of materials only to the semiconductors. Again, the semiconductors are classified into two types. One is called intrinsic semiconductor and second one is called extrinsic semiconductor. Intrinsic semiconductor can also be named as pure semiconductor. Extrinsic semiconductor can also be named as impure semiconductor. First, we need to understand what is the difference between a pure semiconductor and impure semiconductor. The pure semiconductors are not popularly used for practical applications. Let us discuss why these intrinsic semiconductors are not preferred for practical applications. Now, most of the people are listening about the process called dope test. In newspapers, mostly we listen the method called dope test. The players are undergone for a dope test and some players have caught in the dope test. The reason is, suppose if a cricketer is playing a match, which is a very, very crucial match as World Cup. Before that major event going to happen, each and every player will undergo a test called dope test. Why the people are doing a dope test is, let us come back. If a player wants to play 50 overs, it's a cricket one-day match. If the player wants to play 50 overs, start from right from the first over, second over, go on. If the player is playing up to 20th over, the energy levels right from the first over to the 20th over may not be the same. The energy levels decreases with respect to the time or with respect to the number of overs. As the number of overs are proceeding, the energy levels in the player will decrease. But the player wants to maintain the energy level as the same, irrespective of the number of overs or irrespective of the time. You want to maintain the same consistency. You want to hit the ball with the same amount of an energy. What the people will do, they will take a steroid and inject this steroid directly into their body. Before injecting the body is a pure body, but there is a limitation. After some time, the energy levels are going to decrease. What people will do, to the pure body, they will take a drug. These drugs are injected, or the steroids are injected into the body. These drugs or steroids are called as impurities. If these drugs are injected into the body is going to be becoming impure. But the energy levels, when you compare over the pure body, here in the impure body, the energy levels are very, very high. The same reason is valid for the semiconductors. In case of an intrinsic semiconductor, you call it as a pure form of a semiconductor, where the conductivity is very, very less. That is why intrinsic semiconductors are not practically preferred. Whereas in case of extrinsic semiconductors, you are trying to add impurity atoms, you try to add impurities, the conductivity of that particular material will also increase. As a result, extrinsic semiconductors are used in practical applications. Now, let us go through the basic covalent band structure or the crystalline structure of silicon atom. Now see here, it is making a covalent bonding. The silicon atom is having a covalent bonding with the adjacent silicon atoms with the help of 4 valence electrons. The valence electrons are the electrons which are there in the outermost orbit of an atom. We call them as valence electrons. In case of silicon, we have 4 valence electrons. These 4 valence electrons is going to be making a covalent bonding with the adjacent silicon atoms. There you have a complete covalent bond structure that will appear. If you apply some external energy, some of the covalent bonds are going to break. Let us say here some of the covalent bonds are going to break. What will happen? The valence electrons which are there in the covalent bond, they will come out from the covalent bond and they will become as a free. Let us think that here I have a valence electron. If external energy has been applied, it will gain that energy. It will come out from that covalent bond. Now it will become as a free instead of staying in the covalent bond structure. Now it will create a vacant space here. If it creates a vacant space here, the vacant spaces are called as holes. If that valence electron come out from the covalent bond, now these valence electrons are named as free electrons. Now the free electrons are capable of moving freely inside of the material. At any point of time in intrinsic semiconductor, the number of free electrons and the number of holes are always equal. This is one important point we need to remember in case of an intrinsic semiconductor. The total number of free electrons and the total number of holes that are generated in an intrinsic semiconductor is always equal. See, you don't apply any external energy. You call at absolute zero temperature. Intrinsic semiconductor behaves like an insulator. And you try to apply an external energy if the valence electrons coming out from the covalent bond and becomes as a free electrons, creating a vacant spaces in the covalent bond structure. At any point of time, the total number of free electrons and the total number of holes that are generated in an intrinsic semiconductor are equal. That is represented with the concentration of electrons is equal to concentration of holes, which is equal to Ni. Ni is representing intrinsic concentration. Now, let us come to one more definition which is related with this, called thermal generation. Due to the external temperature or external voltages, you try to apply, the charge carriers are going to be absorbing the energy and they have the sufficient energy to break the covalent bond and to come out from the covalent bond and to become as a free electron. Whenever it becomes as a free electron, if a valence electron becomes as a free electron, it will create a vacant spaces. You try to apply more amount of an energy, the number of free electrons and the number of holes are also going to increase. The process, this particular process called generating or creating the free electrons as well as the holes is called thermal generation. We have already mentioned at any point of time, the total number of free electrons and the total number of holes are always equal. If I have one free electron, one hole is created. If I have 4 free electrons are there, 4 holes are created. That is what is the basic principle in case of a thermal generation. Now, one more definition we need to understand in the concept of semiconductor is a drift current. This is the amount of a current that has been produced due to the drifting of the charge carriers inside of the material is called the drift current. If the electron changes its path during its traveling inside of the semiconductor, that is a very simple phenomenon. If a free electron is traveling on its way, if a silicon atom comes on its path, it is go and collide, then it will change its direction. Before it is colliding, it is traveling with a velocity, let us say v1. After the collision, the electron is going to be changing its direction. And at that time, the velocity will be different. It's a random velocity. And the electron is going to be moving in a different direction. This is what is a simple method that is going to be indicating the process of drifting. If that electron is moving in a random direction with a random velocity, it is going to be producing a current called drift velocity, and the velocity with which the electron is going to be traveling inside of that material is called drift velocity. Another process is called as a recombination. We know that if there is a thermal generation, means that free electrons and holes are created in pairs and the free electron is traveling inside of a material. Suppose if it finds a vacant space called as a hole, it is go and combine with the hole. What will happen here is the both free electron as well as the hole are going to disappear. If recombination rate is increasing, the meaning is that the free electrons are continuously combining with the corresponding holes. As a result, both free electrons as well as holes are vanishing from the material. If recombination rate is more, the conductivity property inside of the material will also going to decrease. And one more definition which is related with both thermal generation and recombination is mean lifetime of a charge carrier. We know that the charge carriers are created, they are born, just like They are born at a phase called thermal generation. They are created at thermal generation and they are going to be vanished at a process called recombination. The time gap between the thermal generation and the recombination is called as the mean lifetime of a charge carrier. How much of a time the charge carriers are going to alive between the thermal generation and recombination. Suppose if a free electron has been generated due to thermal generation. Now at a time t1 it has generated. It will move inside of the material at a point of time called t2. That particular free electron is going to combine with a hole and the process is called recombination. At this point both hole as well as the free electrons are going to be vanished. And how much of a time the charge carriers has appeared between the thermal generation and recombination is called as the mean lifetime of a charge carrier. That is the basic definition called mean lifetime of a charge carrier. One more important definition is law of mass action. The law of mass action states that the product of free electrons and holes is always constant at a fixed temperature. Let us imagine that there will be a temperature called T1. At this particular temperature, let us say this is also a form of an energy called thermal energy. There are n covalent bonds that are capable of breaking. If they are break, the number of free electrons and the number of holes are equal. We know that. And what this law of mass action states that the product of electrons and holes is always constant at a fixed temperature. If the temperature is not changing, if the temperature is fixed, and the number of holes and number of electrons that are going to be generating is always a constant. That's what is the definition indicates. The product of free electrons and holes is always constant at a fixed temperature. That can be indicated with Np is equal to Ni square. We know N and we know P. We know N and we know P. N is equal to P, which is equal to Ni. And here the product of free electrons and holes, N is equal to P, which is equal to Ni. If it is a product of electron and a hole, it is Ni into Ni that gives you Ni square. Np is equal to Ni square. This is the basic equation for law of mass action.